Page 21. So basically, we're going to deal now with modeling data. So we're going to have to do regressions that involve exponential functions. So I'm going to do one with doubling time and one with half-life. They each work very similarly. So once I have doubling time down, you'll get the half-life as well. So a certain strain of bacteria is being observed in a petri dish and is known to have a doubling time, right? That's very important, doubling time of 7.5 hours. If the initial population of bacteria is 2550, determine the equation that would model the situation. I would just say this. Population growth, doubling time, or half-life. All of those you should right away imagine that this is going to be most likely exponential. Right? Growth happens exponentially. I'm sure you've covered it in other courses. Right? When you talk about population growth, it's exponential most of the time. Not always. Sometimes population decreases. That is also something we're going to talk about. But we're talking exponential regardless. So we want the equation that models the situation. Because of the doubling time, we're going to have time in hours compared to population of bacteria. And the very, very important start is that at time 0, what do you have at time 0? You have 2550. Okay, this is your initial population. And that every 7.5 hours, we're going to add 7.5, which gets us to 7.5. We're going to double what we had before. So we are at 5100. And you should do it one more time. Sometimes it tells you, sometimes. So another 7.5 hours go by, so that'd be 15 hours total. You double what you had previously again. So that's 10,200. And that's good enough already. Okay, so we're going to type this into L1, type this into L2. We're going to call this X and Y. Let's go and grab our calculators and perform the regression here. We're going to go stat edit like before, clear whatever is in there, and then just enter those values. 0, 7.5, 15, 2550, 5100, 10,200. And so now we perform our regression. So we got to go stat, calculate, and you have to look for it. It's way at the bottom. It's option number 0. So you got to go past the last option. And there it is, exponential regression. So I'm going to just make sure we understand. Stat, calc, exponential regression. And I'm going to come up with my equation here. So enter. We go second 1, comma, second 2, comma, alpha, trace. Let's plug it into Y1. Here it is. 2550. 1.0968. I'm going to use 4 decimals. You could do 2 to the x. Right? So this is your exponential regression. And I hope that you understand if something has a doubling time, that there's an increasing effect, right? If you double what you had previously, you're increasing. We are looking for this to be greater than 1. Is it greater than 1? Right? B is greater than 1. That's good. Does the 2550 make sense? Yeah, it's our initial population. This is your y-intercept. So you want to check to see if things are, in fact, what they should be. So we're good. What is the population after 36 hours? No problem. It doesn't say days. It says hours because that's a classic that oftentimes they won't necessarily use the same units, but we have them. So second trace value, x is equal to 36. We'll figure out what y is. So we first need to graph this. Sure, you can go to y equals and turn on plot 1 if you'd like. It's probably going to help you. So I'm going to try zoom stat. There it is. Actually does a pretty good job in this case. I'm just going to make sure that my x-axis is actually visible. So I'm going to go window. So my y min, it's a little too high. So I'm going to go -5 or -10, something just below the x-axis. Graph it one more time. So this is better. Now let's go find this value here. I should probably check my window one more time. X max is 16. I'm going to enter 36. It's probably not going to let me, so I'm going to change this to 50, let's say, and hit graph one more time. So let's see if this works. Second trace 1, 36. It did let me find it, but it's way up in the 71,000 range. I'm just going to write this down. Right, that's what I get. So it's approximately 7136 bacteria. I will increase my Y max because it's just not a good. So Y max, I'm going to go 100,000. There we go. That's one of the characteristics about an exponential, that at first it flattens a bit and then it shoots up rapidly. Right? So we've got that. How long will it take for the bacteria population to reach 14,500? Right, so they're asking, hey, what's the time if this is 14,500? So I let y2 equal 14,500, and then I find the intersection between those two lines. And x is going to be 18.81 hours. If you put units and just one number like that, you're good to go. Just don't give me coordinates and don't state specifically which one it is that we're looking for. State one limitation of the equation in A. So this model right here, what's a limitation of this model as is? Do you think the population will just keep growing indefinitely if you're in a petri dish? There's only so much space, correct? And then bacteria is actually going to start decreasing after a while. So this is probably only true for a certain amount of time, not into infinity, right? So that is what I mean here. There's a bit of a restriction placed on the fact that this just keeps growing indefinitely. So I'll say that. As is, the time and population is increasing indefinitely. indefinitely. This cannot be, since the Petri dish will at some point fill up, causing the bacteria, I guess preventing the bacteria to grow further. Something like that. You just say that you can't go indefinitely, right? Even if you looked at a tree, it's like, hey, this models the growth of this tree, and it's like, yeah, well, it will be true for a while, but at some point the tree will stop growing, right? So that's what I would ask you to kind of highlight in this case. Here you go. If the maximum capacity of the Petri dish is 95,000 bacteria, state the domain and range. There's only so much that it can handle. So let's go find, right? We're going to say, okay, if my bacteria is 95,000, what is the time? How long will it take for that to happen? So I can trace 5 for that. And notice I already changed my window. You might have to change it accordingly to make 95,000 fit. Right, so let's see, yeah, this works. So it's right there. That's when it's going to stop growing, okay? Second trace 5, enter, enter, enter. And it is 39. I'm just going to write down the whole thing. 39, 15, 95,000. So if you want a little, right, this is 95,000 right here. And so this is the point you just found. So for my domain, that's time. And there's a range, which is the population. What's your domain here? Starts at time 0, and it stops growing after 39.15 hours. Right, this is my time that we're talking about. And then population, is it 0? It's not 0. What's the lowest we ever get to? It's 2550. Okay, 2550. This right here is 0, 2550. It's very important. You don't start, if you don't have any population to start with, you're not going to grow, right? So there we go. And then the maximum we're told is 95,000. This is population. That's your domain and range in this case. Hold on. I will make that note again. Okay, I'll make the note again that I made yesterday. If this statement had not been made, that there's some sort of stop to the growth, you would in fact go infinity. Okay, it has happened, right? So I'm gonna go to 22 here. Note, if there is no limitation, then domain would have been 0 to infinity. Your range would have been 1550, no, 2550 to infinity. And then the graph would have you actually would have been okay to just say, right, that the arrowhead just keeps going. Fun stuff, eh? Some of you are going to use this in post high, whatever you're doing after high school. You might look at exponential growth in whatever you're doing. We're good? Okay. I'll do another one which has half-life. Can I just say, let me go back to doubling. Doubling time is definitely increasing. Okay. This is on page 21. If you're talking doubling time, guess what? You're increasing. You keep on doubling. Okay. But if it's half-life, you're decreasing. Okay. Questions involving half-life. This is on page 23. Decreasing. THC found in cannabis has a half-life of 1.3 days in infrequent users after it is consumed. If the initial amount after consuming a cigarette is 25 nanograms, right? State the exponential equation that would model the level of THC in nanograms in terms of days. Okay. So let's see here. It does tell us to make an exponential. If it's half-life, you can bet on it. So we'll go time, and in this case we have days, and this would be THC in nanograms. Right? Now I have your attention, right? Let's see where this is going. Yeah. Okay. So what's my initial point here? What do you think it's going to start with here? At the very beginning, time is 0, right? When you just consume that cigarette, you have 25 nanograms in your system. And then we're told that the half-life, let's highlight that one. The half-life is 1.3 days. What does that mean? What does half-life mean? Yeah. Exactly. And it takes 1.3 days. So I add 1.3. So from 0 plus 1.3 is just 1.3 days. This will be down to half. So you literally divide it by 2. So that would be 12.5. Another 1.3 days go by. 1.3 plus 1.3, that's 2.6 days later. It'll be down to half of what it was before. And that is 6.25. That's good enough. It could be that the question asks you for 4 half days, half life cycles, but 3 is good enough. So now we have L1 and L2. This is my X and my Y. Let's go ahead and find our equation. Stat, calc, exponential regression. Okay, so stat edit 0, 1.3, 2.6. It's 25, 12.5, 6.25. I double check. I didn't miss a decimal or anything like that because that's very frustrating. I got it. I have this on my screen somewhere. I'm just going to go copy paste. There it is. Just run that program again. And here we have it. Y is equal to 25, 0.5867 to the X, right? That is your perfect. This is my initial amount, 25, and we know that the amount is decreasing because this is less than 1, right? So then we know 2 things right off the bat. How long will it take for the THC level to be 5 nanograms? I'm thinking if I should talk, I will give you a bit more here. What does this mean? Okay. If you go 1 minus that, you get 0.4133, which is the equivalent of 41.33%. What is this? This is telling you that the THC is decreasing by 41.33% per what? This is the magic word here. Is it per hour, per day, per year? It is per day in our case. We're talking day. Okay, so if you wanted to know what it is per day, then this is important to understand. I would have talked about that at the very beginning, introducing exponentials, right? But inside the bracket, you can figure out, using that number, you can figure out what percentage you're either decreasing by or increasing by. It depends on, right, whether this is greater than 1 or less than 1. So this is actually a very important concept that this question is not asking, but I think it's very, very important for you to know. The level of THC is decreasing by 41% or so per day. Okay. How long will it take for the THC to be 5 nanograms? And remember, this, they're giving you this. We want to know how long it will take. So let's graph this. I have a feeling that if I use my previous window, this is way off. So a couple of things you can do. I'm going to clear everything like Y2. I'm going to clear that. You can do zoom stat. Why not? There it is. We expected it to decrease. Okay. I'm going to expand my window. I'm going to make sure I see more to the right, and I also want to see the x-axis. So my Y min, I'm going to go -2 or something like that. Y max seems to be pretty good. X max, let's extend that as well. I don't know, 10 days. Let's try that. Hopefully after 10 days, the THC is gone, right? Hopefully. There it is. So this is a pretty good window here. Let's go find this. So Y2 is equal to 5. And there it is. So we're going to go find that intersection. I will just write Y2 is equal to 5. Second, trace 5. And it is x is equal to 3.02 days. If it asks you to find it in days and hours, you just multiply whatever is after the decimal by 24. So it's 3 days and right 0.0185 something times 24 to get that in hours as well. So there you go. If having a THC level of 2.5 or above is considered impaired driving, how long would an individual have to wait before driving? Okay, let's find that out. This is probably not realistic. 4.32 days. Yeah, right. I feel like this should have all been hours. I'll have to double check that. The limitations of the equation in A. that's the limitation of this one in particular. Do you remember, this was last week, I don't know if you did it over the weekend. Does this line ever touch the x-axis? Do you remember me zooming in on the, do you remember me zooming in and it never touched? Is that realistic? Will the THC level never reach 0 in your body, ever? It's not realistic. At some point, it will be 0, right? If you stay off of it for long enough, it will be. So that's a limitation here. Okay. A decreasing exponential, actually, no, doesn't matter. It doesn't matter if it's increasing or decreasing. Sorry, I don't want to mislead you. It is decreasing in this case, but an exponential function never crosses the x-axis. In this case, it would not be realistic as the THC levels will at some point reach 0 ng. Okay. By that, but what I mean by that is, even if you start at 25 nanograms, at some point, we don't know when, right? But at some point, you will reach 0 nanograms. We don't know the time. We could, I guess it's, in reality, they probably know exactly when that is. But it does reach, it would cross the x-axis at one point, but this doesn't do it. Okay. All right. So, for homework, I'm actually going to go back in time a little bit. Like some of the questions I assigned yesterday had this happening. So I would say pages 19, 18 and 19. There's one half-life and one doubling time, as well as, I don't want to be hanging without anything to do, right? So this booklet has a lot of questions you can practice. I would say page 25 has something like this as well. Pages 30 to 31. But I will post everything in between as well. Can I just say one thing about, I may not have covered it today, but you essentially did that. Sometimes the questions just flat out gives you the table. You don't have to create one. We created ours because we were given the doubling time or the half-life. So just remember that you can also be given a table, and then you might have to figure out what the half-life is. What is the half-life? So you have to base it on what you start with, right? Or doubling time. You always base it on what you start with. Can I say that one more time? The half-life, if you see this number, the half-life would, right, you would let y2 equal to 12.5 in this case, right? Half of what you started, and then you could figure that out. If it's a doubling time, you let y2 equal twice of what you started, right? It would be 50, right? If it is a doubling time scenario where it increases. So that's how you find it, just like on the AC today. Okay. All right, that's it. You can get started on maybe 18. See if you have 10 minutes.